Hello everyone and welcome to the session 2 of the hydrogens JEE and NEET class. Okay, so for today we are going to continue from the question number 26 to 25 more. We'll end up with the 50 questions for today. So let's get started and let's see what questions we have for today. Hydrogen, by donating one electron, forms H plus ion. In this, the property it resembles with. Okay, fine. Now, if you observe the question number 26, okay, so what they say is hydrogen has a tendency to lose one electron in order to form H plus ion, and hence it is going to lose one electron. Correct. Now, the same particular type of properties are exhibited by, it's not the transitional metals. Transitional metals are the particular metals which can give even 2 or 3 electrons. Okay, the oxidation state varies from +2 to +7. Okay, now in alkaline earth metals, what happens in this particular case is these particular metals have a tendency to lose 2 electrons. So +2 is the state over there. While alkali metals such as the sodium, potassium, lithium and all, these particular metals have a tendency to lose just 1 electron. So when it loses 1 electron, we are going to get an oxidation state of +1, which is similar as that of our hydrogen states. So here the hydrogen, after losing 1 electron, it attains an oxidation state of +1, as what we have similarities with the alkali metals. Right? So therefore, the option is C in this particular case. Moving towards the next question, question number 27. Ordinary hydrogen at the room temperature is a mixture of. Now, hydrogen is a mixture of 2 allotropes. Right? So, the 2 allotropes, we already know them as being an ortho hydrogen, wherein the spins of the protons, the proton spins, the nuclear spin, are in the same direction. While in the case of, if we see with respect to the protons, over here with para. Okay, so in the case of the para hydrogen, what happens is, in this particular case, the spins are in opposite direction. Both the nucleuses are in opposite spins, right? So, ortho at the room temperature, it constitutes of around 75%, while para constitutes around 25%. We are speaking this with respect to the room temperature only. Okay, so in this particular aspects, we have the option 1 as 75% of the ortho hydrogen and of course 25% of the para hydrogen. The next question number 28. Which of the statement is not correct for the ortho and para hydrogen? Okay, so A option, they have the same boiling points, which is actually not correct. Okay, ortho form is more stable than the para form. Okay, now if you observe this particular thing here, okay, in the option 1, they both of them have a same boiling point because both of them at the end they are hydrogens. Okay, but here in this particular case, wherein the stability is concerned, one thing that we have to remember is that the ortho hydrogen, this ortho hydrogen is more stable than the para hydrogen. Okay. At a condition, the condition is that above the room temperature, that means at a higher temperature, we have the ortho hydrogens which are more stable than the para hydrogen. Okay. At the room temperature and at the lower temperatures are been concerned, we have the para hydrogens which are more stable than the ortho hydrogens. So this is a new point what we have to remember now. So ortho hydrogen is more stable only and only above the room temperature, and so therefore this is an option, that is option B. okay, which is actually not correct. Okay, towards the question number 29. So, ortho and para hydrogen resembles in which of the following properties? Now, thermal conductivity for the ortho and para are different. Okay, so therefore, thermal conductivity cannot be an answer. While magnetic properties, again, they depend upon the spins. Okay, so therefore, as the spins are different, the magnetic properties are going to be different. Therefore, option B is also not a correct one. What they have is the option C holds the correct answer, that is the chemical properties of ortho and the para hydrogens are similar. Okay, I'm not saying they are same, rather they are similar. Okay, they resemble in that particular properties. Moving towards the next question, and the question number 30. Ionization energy of hydrogen is now. When we were studying about the ionization and the properties of hydrogen, which are similar to that of the halogen, we came across one important point, and that important point, as what we had come across, was about the ionization enthalpy. Now, ionization enthalpy for the hydrogen was, okay, there the energy as what we had got was 1312 kilojoules per mole. Right? While when we take a look into halogens such as the chlorine in this particular case is concerned, okay, when we have the same thing for chlorine, the chlorine exhibits an ionization enthalpy of around 1255 kilojoules per mole. Okay, that means hydrogen has an ionization enthalpy slightly heavier, slightly higher than that of the chlorine. Okay, so therefore, ionization energy of hydrogen is going to be slightly higher than chlorine. With the question number 31. Hydrogen has 3 isotopes. The number of possible diatomic molecules will be, okay, it has 3 isotopes. So the 3 isotopes can be said as protium, deuterium and tritium. Okay, so now possible diatomic molecules means you are going to take particular proton, attach it to proton and see one molecule. Okay, so here possible combinations can be as protium and protium, this is one combination. Protium and deuterium, this is the second combination. Protium and tritium, this is the third combination. Okay, let's go with the second one, that is deuterium. Taking into deuterium and deuterium, this is the next possibility. Deuterium and tritium, this is the next one. Okay, now if I am going to take as deuterium and protium, it's already been mentioned. Okay, so we are not going to go with that. Now what remains is the last one with respect to tritium. So tritium and tritium. So the number of isotopes that what we have now are going to be 1, 2, 3, 4, 5 and 6. So therefore the option B is a correct one in this case. So the next question, question number 32. Triatomic hydrogen has a name, and that particular name is called as the Hydra zone. Remember this, triatomic molecule is called as the Hydra zone. Okay, we already know about deuterium. Deuterium is nothing more than 1H2, right? Okay, ortho form is nothing more than an allotropic form. While when we observe the hydronium ion, that is H3O plus. Okay, so therefore what remains is option B in this particular case, and that is going to be the hydrozone. Coming towards the next question, question number 33 is what we have here. Out of the two allotropic forms of hydrogen, the form with lesser molecular energy. Coming back to the same one, that was the allotropic forms of hydrogen. So, when we take a look into the allotropic forms of hydrogen, okay, what we have is the two forms. The one is an ortho, and of course the other one is the para. Okay, in the para, what happens is because of its opposite spins, okay, this particular allotrope actually has lesser amount of energy when we compare to its ortho form of hydrogen. So, it's actually the para form. Okay, meta does not actually exist with respect to the allotrope of the hydrogen is being concerned. So, therefore, B is not an option. Of course, D, again, all of them have same energy. We cannot predict that particular thing. So, therefore, D is not the correct answer. So, coming towards the question number 33, metal hydride on treatment with water gives. Okay, let's take one example before coming towards the option directly. Okay, so let's take one example such as potassium hydride. Okay, and now what we are saying is the metal hydride is going to react or on treatment with water. So therefore, let's say that what we have here is reaction with H2O. Correct? So now, upon the reaction with H2O, what happens is this particular potassium reacts with water in order to form potassium hydroxide. The total number of hydrogens, as what we have here, is one hydrogen here and two hydrogens here. That means there are completely three hydrogens. Right? Out of three hydrogens, we have used one here. What remains with us is two more, which are going to get evolved in the form of gas. Okay, so therefore, what happens now is metal hydrides on reaction with water, it actually gives us hydrogen. Now, let's observe this particular case. This particular case, where we have written as H2O2, is nothing more than hydrogen peroxide. Okay, so hydrogen peroxide it has a structure as this is the hydrogen peroxide with the two hydrogens over here one, and two central oxygens. So that was your hydrogen peroxide. Of course, we know what is an acid. An acid is nothing more than a substance which donates protons. When we take a look into the question number 35, in which of the following compound the hydrogen has an oxidation state of -1? Remember one thing, that is, whenever we have a hydrogen and the hydrogen is connected to a metal, okay, it is going to drag the electrons, making itself a electronegative, okay, whereas the metals are electropositive in their natures. So therefore, find out the metal. 1, 2, 3, 4. In all the four options, we have calcium here, that is the metal. Okay, so therefore, when we have CaH2, for a moment, let us say that this calcium here, okay, has an oxidation state of +2. I do not know anything about the oxidation state of this particular hydrogen, so I will place it as X. Okay, now whenever the two things are going to combine, it is going to have a neutralized value that is equal to 0. So therefore, let's say +2 of calcium plus 2x. Why it is 2x? Because we have two hydrogens here and that is equal to 0. Okay, so therefore +2x is equal to, let's send this particular thing to our right hand side, so it becomes as a -2. X is equal to -2 over 2 and that is equal to -1. So therefore, what we have here is the calcium hydride. Okay, so calcium hydride is nothing more than the compound wherein we would find an oxidation state as -1. Okay, in CH4, you would find that the electronegativity of hydrogens and carbon are almost the same. Okay, so there are no much of the charge differences there. While in NH3, because of the higher electronegativity of nitrogen, it pulls the electrons from the particular things, that is from the electrons that are shared between the hydrogens and the nitrogen. Okay, it is going to be pulled out. So therefore, the hydrogen suffers from the less number of electrons there. As a result of which, the hydrogens over here are going to get a positive charge, +1. The same occurs here, that is, wherein the hydrogen is connected to the chlorine. Okay, chlorine being more electronegative, it pulls the electron towards itself, making it electronegative, and this, of course, is going to get positive. So, there is no point in having an oxidation state in the positives, in the case of 1 and 2. Okay, so therefore, our answer lies with D. Forward with the question number 36. Deuterium resembles hydrogen in chemical properties but reacts. Now, they are asking us about the reactivity between the deuterium and simple hydrogen. Okay, now remember, as this particular deuterium, which is an isotope of hydrogen, is having one neutron. Okay, so the presence of one neutron makes it heavier. Okay, it makes this particular thing heavier when we compare. Okay, when we compare to that of a simple hydrogen. Due to which, what happens is, in this particular case, it is going to have lower frequencies of vibration. It cannot vibrate much more faster when we compare to that of the hydrogen. As the vibrations are lower, its reactivity is also lowered. So it has a direct influence on the reactivity. Okay, so when we compare hydrogen and deuterium, deuterium being more heavier than hydrogen, it has that effect directly on vibrations. As the vibrations are affected, its chemical properties, its chemical reactivity, the rate of chemical reaction in this particular deuterium is reactive. Okay, it is going to be affected. Therefore, what will happen is, deuterium resembles hydrogen in the chemical property but reacts slower than hydrogen. It all because of its heaviness, or it's because of its weight has been concerned, and therefore option C, it is in this particular case. Question number 37. Protonic acids is, okay, let's see, option A, a compound that forms solvated hydrogen ion in polar solvent. Okay, an acid which accepts the proton. Alright, a compound that forms hydride ion in polar solvent, an acid which donates proton. Okay, so protonic acid, let's take one example over here for protonic acid as, let's say, HCl. Okay, so protonic acid, when we put this thing into polar solvent, let's say in polar solvent, as according to A, what it shows now is acid has a tendency to donate proton. Okay, so this particular proton adds up to water in order to give us H3O plus. Okay, plus what we have is Cl minus. Now, what it is doing? A compound that forms solvated hydrogen ion in polar solvent. Okay, so therefore, it is actually this. In polar solvent. Okay, this is a polar solvent, water. Okay, so what is happening? Proton is getting transferred to the polar solvent, and therefore it is forming a solvated hydrogen ion. Over here, it is forming a solvated hydrogen ion. Correct. So therefore, the option A is a correct option. option in this case, while the next options do not give us a perfect explanation. Coming towards the next question, syngas. So here, syngas is nothing more than water gas itself. Okay, so another name for water gas, you can call it as a syngas. So a syngas or a water gas is a variable combination of carbon monoxide and hydrogen. So therefore, in that particular case, if you see carbon dioxide plus hydrogen, no. Carbon monoxide plus hydrogen is actually the correct answer. Okay, so therefore, B, that is carbon monoxide plus hydrogen, is actually a correct answer for syngas. Coming towards the next question, temporary hardness of water. Now they are speaking about the temporary hardness over here. Temporary hardness of water is caused due to the hydrogen carbonates or bicarbonates, as what we can say. Okay, now this bicarbonates in combination with either calcium ions or with the magnesium ions, it is going to cause us the temporary hardness of water. Okay, now they are asking how we can remove those. So, addition of potassium permanganate is not going to affect the bicarbonates. So, we do not have this. A simplest form is by simply boiling. You cannot filter because of its higher solubility. Okay, these particular ions are highly soluble in water, so therefore filtration is not going to make any change. Again, addition of chlorine, which converts or which makes chloride ions. Chloride ions, again with the combination of such kind of ions, is going to make that particular water permanently hard. So therefore, what option we have is nothing more than the boiling of water. Okay, so in the boiling of water, what happens is, if I'm going to take over here CaHCO3 twice. So as we take it and as we hit it. Okay, so what forms is calcium carbonate along with the elimination of H2O, water, and carbon dioxide. Okay, so this is what we get on boiling. So therefore, calcium carbonate, which is formed upon boiling, it precipitates down. Okay, forms the powder, precipitates down. We can simply filter it after boiling the particular water. Okay, and then we will end up having a soft water. Coming towards the next question, and that is the triple point of water. First thing is that what exactly is a triple point? Okay, now triple point is nothing more than a particular condition of temperature and pressure wherein all the three states of water coexist simultaneously. That is, at a temperature, we have a solid form of water, that is ice. We have liquid form, that is water, and we have the gaseous form, that is nothing more than the vapor. Okay, all of these are going to be available at a particular temperature simultaneously, and that particular point we call it as a triple point. Now the temperature is nothing more than 273.16 Kelvin. Okay, at 0.0611 atmospheric pressure. At this particular pressure, what happens is we are going to have water triple point, wherein water exists in all the three phases simultaneously, and therefore the option 1 is correct. Next one. Which of the following is a use of alum? First thing we need to understand is what exactly is alum. Okay, now alum is usually represented as X dot. KAl2.12H2O. Now, this is nothing more than an alum. Usually we get it as a combination of potassium as potash alum. Okay, wherein we directly replace X by K. So therefore, potash alum will be as KAl2.12H2O. Alum is usually used in order to soften the water. It removes the hardness of water by exchanging the ions. So therefore, in this particular case, it is used just for water softening. Okay, that is the use of alum. Okay, so coming towards the next question, question number 22. 1 mole of calcium phosphide. Calcium phosphide is nothing more than Ca3P2. It's called as calcium phosphide, which on reaction with excess amount of water, it has a tendency to give us phosphine. Phosphine is pH3. Okay, is plus CaOH twice. So therefore, if we try to balance this, we have 3 here. Okay, we have to balance this as 6. Therefore, 2 phosphorus here, so 2. So upon hydrolysis of phosphine, upon hydrolysis of this particular calcium phosphide, we get 2 molecules of phosphine. Okay, so therefore, it is the option, actually the 2 moles of phosphine, that what we are going to get, and this is the correct answer. Okay, so the next question, question number 43. Which among the following is a hydride? So now they have directly given us the names. First, we shall convert these particular things into their molecular formulas. Okay, so formula for this particular thing, first one, that is the rogalite. For rogalite, what we have is actually a salt of sodium, OH, H2, SO2 minus. Okay, so rogalite has this particular chemical formula. It is a salt and it's not a hydride. Okay, nitroleum. Nitroleum is CaCN2. Okay, so CaCN2, calcium cyanamide. Okay, cyanamide. So this is again not a hydride. While when we take a look into the hydrolith is CaH2. That is a hydride of calcium, which is called as hydrolith. Now, what we have is the last one, that is minimum. We have as Pb plus 2 twice Pb plus 4 O2. This is a combination which is also called as the red lead. Okay, so this is the red lead over here. Again, this is not a hydride. So hydride is just hydrolith, which is the calcium hydride in this case. Question number 44. Tritium is a radioactive isotope of hydrogen. Yes, it actually emits the beta particles over here. Okay, so the emission of radiation contains beta particles. So remember about tritium, that is, it is a radioactive material which emits beta particles. Going forward with the next one, and that is a very simple thing. That is the HOH, that is the angle in water molecule, HOH. Now this particular angle in water molecule, due to the lone pair of electrons which causes the bent structure, this particular angle is 104.5 degree, right? So therefore, option is D. Towards the next question, which property is shown by the following reaction? So So here, if you observe Fe3O4, that is the ferric chloride, that is it is the ferric oxide on reaction with 4 molecules of hydrogen. So here, if you observe this thing, this particular hydrogen is taking away oxygens. It is taking this oxygens in order to form the 4 molecule. Right? So now, this hydrogen is reducing this entire sequence. It is removing out the oxygen. Same is the case in this particular form. That is, carbon monoxide reacts with the hydrogen gas in order to give us CH3OH, which is a methanol. Okay, so in this case also, there is a process of reduction. It is attaching hydrogen. So, reduction is a process wherein either you remove oxygen or either you attach hydrogens. Okay, so therefore, it is acting as a reducing agent in this particular case. So, option is A. Okay, so coming towards question number 47, which of the following represents Clagon? Now, Clagon is nothing more than sodium hexametaphosphate. Okay, so there should be 6 sodiums and a phosphate section. So if we observe that, this is noted, that is Na2Al2Si2O8, that is a sodium aluminum silicate, which is a zeolite. Okay, this is not correct. Mg3PO4 twice, not correct again. What we have here is this particular form, that is 6 sodiums. Sodium hexametaphosphate. Okay, so therefore option C is the correct one for Clagon. Coming towards the next question, question number 48. The formula for the exhausted permit is, now in an ion exchange process, what we had seen was, because of the presence of calcium and magnesium, okay, these particular ions are replaced by sodium. Okay, so therefore in an exhaust permit, it's the sodium which goes into the water, and from the water, the particular ions which are causing the hardness, they are being removed. And those particular ions are nothing more than either calcium or magnesium. So we need to search for that particular option which has either calcium or magnesium in its composition. So therefore, if you observe the first one itself, hydrated, this is a hydrated section of, it was actually sodium aluminum silicate, zeolite type of method, wherein sodium has gone out and calcium has come inside. So therefore, calcium aluminum silicate, hydrated one. Okay, this is actually sodium aluminum silicate, which is a zeolite. Okay, so therefore, that's not a correct answer. Neither this one, neither this one. Okay, so therefore, option is A, that is a calcium aluminum silicate, because of the exchange of ions from water to the zeolite. Okay. Coming to the next one, a fact-based question, and that is, on burning the hydrogen in air, the color of flame is going to be a bluish, that is a slight bluish in color. Okay, so coming towards the last question for this session, and that is, how do we measure the degree of hardness of water? So, degree of hardness of water doesn't matter whether the magnesium are present or the different types of calcium salts are present. It's always measured in the terms of the ppm, that is the parts per million of calcium carbonate. Okay, divided by the weight of the calcium carbonate. So therefore, it is actually the option C, that is the ppm by the weight of calcium carbonate, irrespective of whether the calcium carbonate is present in that particular hard water. Okay, doesn't matter. Even if there is a magnesium sulfate, magnesium chloride, okay, in that particular case also we measure the hardness of water with respect to the calcium carbonate, even though if the calcium carbonate is present or absent, it makes no difference. Okay, so therefore it is defined by, or it has been defined by the degree of hardness of water is expressed in the terms of the ppm parts per million by the weight of calcium carbonate. Correct? So, for today, we end up over here. Take care and have a great day.